Hello and welcome to this Dynaflow webinar where we'll show you how to use FEPipe to help you in solving dynamic and buckling analysis. So the aim here is to show you how to use FEPipe to help you solve these two types of problem. Today we're going to cover a brief introduction to what is buckling and what type of dynamic problems might you come across. And then we're going to show you with the combination of slides and examples how to use FEPipe to solve a buckling and a dynamic analysis. So Dynaflow Research Group and Pauling Research Group, the manufacturer and maker of FEPipe, have worked together since the late 1980s. And Dynaflow Research Group is a large user of FEPipe in our consultancy work for the oil and gas industry. The two companies also collaborate together on software development. And using our consultancy experience, Dynaflow Research Group also provides training courses in FEPipe across the globe. So, what type of problems might you come across where buckling occurs in pressure vessel design? Well, buckling occurs due to an excessive compressive stress. And here on this slide we show you two examples. On the left we show you the case of a railway wagon where vacuum conditions have been reached inside the pressure vessel, and this has caused a collapse of the pressure vessel due to the excessive compressive stress in the hoop direction. See on the right you see an I-beam which has been subjected to a bending moment, like so. This is bending moment, and this leads to a tensile load on the upper surface, on the upper flange. On the lower flange you see a compressive stress, and due to this compressive stress buckling has occurred. And here are three further examples. For example, another storage vessel which has been subjected to a very low pressure, lower than designed for pressure, has caused collapse on one side. And you see on the right, you see a low internal pressure has caused buckling in the head of a pressure vessel. And here you see the web is buckled within a structural steel beam. Now, two types of buckling we're going to talk about when addressing the examples in FEPipe. Talk about Euler column buckling, and this is buckling across the whole length of a column. You see the column here, cylindrical column, has been loaded with a compressive load, denoted by the arrows. When this load P exceeds the critical buckling load, then the first buckling mode will be excited. That is this half sine wave buckling. If the second buckling mode is excited, so when n is equal to 2, then you'll see a complete sine wave, and so on. Okay, and you have more and more complicated buckling modes. Now, the critical buckling mode, PC, is denoted by the equation given here, where E is the Young's modulus, I is the second moment of area, and L is the length of the column. This factor K is dependent on whether this is an anchor or pinned or free. Depends on the fixation of the ends of the column. The second type of buckling I want to talk about is shell buckling. And here you see a vessel that's also been loaded in compression. But here you'll see that column buckling has not occurred given the short length of the column. Instead, you'll see that this local shell buckling, there's a series of lobes or sine waves that run in the circumferential direction around the vessel. So to give you an idea of the general design envelope and when buckling might be a problem, might be the limit for your design, I'll show you this graph. On the left we have applied stress, and on the lower axis we have the L over D ratio, of the vessel. We see on the left we have relatively short stubby vessels, whilst on the right we have long slender vessels. And what you see is for smaller vessels, shorter vessels, then the limit is based on the yield the yield stress of the metal. However, as we go towards more slender vessels, then buckling becomes the critical case, which is donated, your buckling limit is donated by this dashed line. And we see that as we go towards long, thin vessels, then the limit is based on buckling, compressive loads, than that based on yield. Okay, so we've explained a few buckling problems. Now let's look at some possible dynamic problem that could occur for your pressure vessel. Look at the example of vortex shedding from towers. Now, as wind passes around a cylindrical vessel, for example a chimney, then vortices can possibly occur downstream. What we're showing you here on the left is actually a satellite image of the vortices that form downstream of an island in the Pacific. And you can see quite clearly, this is the island, and you see the vortices, the street of vortices that move away downstream. And whether these vortices occur depends on the ratio between the wind speed and the diameter of the chimney or vessel. Often chimneys can create this stream of vortices downstream. And to prevent this stream of vortices occurring, you may see sometimes what's called a vortex breaker on the side of a chimney. And this is a spiral of metal which prevents the formation and the shedding of these vortices downstream of the chimney. Now, why might these vortices be a problem? Well, these vortices have a frequency with which they are shed, and as they are shed, then the pressure distribution behind the chimney will change, and that leads to a cyclically varying force on the chimney. It has a characteristic frequency and amplitude. Now, there exists the possibility that resonance will occur. Resonance is where the frequency of the vortex shedding couples with the mechanical resonance frequency of the vessel itself, the chimney. Okay, and what you can see here on this graph is on the lower axis is the ratio between the frequency of the applied force and the resonance frequency of the vessel. And you see, if these are coupled with each other, then there is a very large increase in the effect of the force compared to the effect if it was applied as a static constant load. This is called the dynamic load factor. And how large this dynamic load factor is depends on the structural damping in the vessel. But typically factors of up to 5 are also possible. So how do we run a buckling analysis in FEPipe? Well, first thing you need to do is you need to run a normal static analysis, okay, as this provides the boundary condition for the buckling analysis in FEPipe. Once you've completed your static analysis, then you need to go to the General tab and you will find the option for buckling eigensolution. And the first step is to change the buckling calculation. You see here that it notes pass 2 run only, which means first run the static as pass 1 and then the buckling as pass 2. And select this yes. And then we need to set the number of buckling modes. How many buckling modes do we want to find? Okay, that's the lowest ones. And then we need to choose the load case from our static analysis that we want to use a boundary condition. So for example, do we want to use weight or the operating case? Once you've set these 3 values, then you can press run and the buckling calculation will be done. Once you've done that, you can then review the output report. Okay, and here you'll see the process. You'll see this iteration, it's the eigenvalue matrix that's being solved, and you'll see this will go through a number of iterative steps until the lowest 6 buckling modes have converged. Okay, and then it will compute and show you the lowest 6 buckling modes for your vessel. Okay, with the buckling load factor, where the buckling load factor is the ratio between the allowable load at which buckling occurs, and the load that you've applied. So a value of 1 means that there's no margin between the applied load and the load at which it will buckle. Okay, so we'll show you an example of how to do the buckling analysis in a minute, but let's also show you how to set up a dynamic analysis. In FEPipe, you have two options for a dynamic analysis, and as with the buckling analysis, these are controlled from the General tab. The first option is to conduct a modal analysis, and here you can determine what are the mechanical eigenfrequencies of your structure. Okay. Here you'll select from the dynamic eigensolution. So as with the buckling solution, you have to turn this on or off, i.e. yes or no. But the difference here is you do not have to first run the static case. You can run this without running the static case. So we select this to yes, and then we can calculate the number of eigenpairs. So we can choose how many eigenpairs we want to calculate. So you can increase this far beyond 6, but then make sure you also could increase the size of the eigenvalue matrix. The second option is to conduct a harmonic analysis. Okay, here you can apply a load, for example, the unbalanced force, the harmonic applied force due to our vortex shedding, to check if it excites a given eigenmode. But just because there's overlap of the forces doesn't mean necessarily that an eigenmode will be excited. Because maybe the direction of the applied force is not such that it would excite the eigenmode that occurs at that frequency. So what we'll do is we'll go to the General tab, and here we can also turn on the harmonic solution. So we'll change this from no to yes. It's important to note that you should also turn off the eigensolution. Okay, and then you need to choose which loads you want to be the harmonic loads. Okay, and these are the loads that you apply normally on the pressure vessel as a boundary condition, but you can choose which loads. So for example, the sustained, the operating, or the occasional loads. Okay, and then it will make all the operating loads in your model a harmonically varying load. And then we can choose the frequency of the applied load. So you can run up to 10 cases in one model. Obviously, if you want more, you could run multiple models. And you need to enter the frequencies of these applied forces. So here we've done a range from 0.1 Hertz to 3 Hertz. Okay, so let's move across and look at some examples. Okay, example 1, I want to show you how to look at the buckling modes that occur in a tower which is subjected to a compressive load. So for example, we're going to just look at a simple case of a column. This is a column which is subject to a weight load of 1 meganewton and has a length of 40 meters, a diameter of 1.5 and a thickness of 10 millimeters. This is a column example, but you could also maybe apply this for the case of a skirt, which is subject to a weight load and maybe a wind moment as well. Okay, so let's now pull up FEPipe and show you how to do this. So we're going to open up FEPipe and we're going to open the model. We've got the model here. Now, what you will see is we'll plot the model and we see we have a long, thin column. If it goes to tabs, we'll see this has a diameter of 1.5 meters, a thickness of 10 millimeters, and a length of 40 meters. Now I've left the shell properties on the default values, so we get the correct modulus of elasticity, but we're not going to do, for purposes now of a standard part 5 calculation, we're just going to look at the buckling calculation. I'm going to set up the shell boundary conditions. At the bottom, we applied a fixicity, and at the top, we applied a force of 1 meganewton, a compressive load of 1 meganewton. Okay, and then what we're going to go to, let's go to the General tab, and we'll look for where the buckling option is. Now what you see now is the buckling solution. should be set to no, okay, because the static case has not been run. So first set this to no, and then we're going to submit and wait. Okay, and now we see that it's calculated the static solution. So if we go to reports, 3D reports, and we see that we've calculated the standard stress template. Okay, now obviously there's no overstress nodes because we gave no allowable stresses up. Okay. But we can go to, but what we do want to look at is a load case report, because we want to see which load case we need to consider for our buckling analysis. So if we go to reports, and we see that the weight case is included in load case 1. Okay, as remember, we put the weight load, the 1 meganewton, as a weight load on the end of the column. So remember load case 1. So now we're going to go to the buckling analysis. So go to general, and now we're going to select here, we're going to select yes, and I want to read out, let's say the lowest 6 buckling modes, and I need to make sure this load case number is 1. I could also change this to be 2, but then I'd have no loads on the end of my vessel, and therefore it would not converge. Therefore, I need to set this to 1 when my weight load is included. Okay. Now we can submit and wait. Okay, so now you'll see it's converged. Let's first of all go to 3D plots. What you see, if we go to the 3D options, you have all the different normal outputs, case 1, case 2, case 3, case 4, and here you have the normal stress options. However, all of these will show the same mode. See, this case 1 is the first order buckling mode. You see we've got a fixed end and a free end. It doesn't matter which case you see, they will also all show the same mode. Okay. These stressors, don't worry about these are just for a visualization. You see the largest stress occurs. If we control this, we'll see due to this buckling mode the largest stress occurs on this side of the vessel, as you would expect. If we then go on to case 2, we'll see the orthogonal buckling mode. As this is a cylinder, there's infinite buckling modes. You can buckle in every single direction. So therefore, 2 orthogonal buckling modes are solved. This is showed by load case 1 and load case 2. If then we go to load case 3, you'll see the more complicated second buckling mode, where you've got free end here, but you see now you're getting 3/4 of a sine wave. Okay, and that will also have an orthogonal component in load case 4. And then if we go to load case 5, you see a more complicated shell type buckling mode. Okay, and we can also change the scale, like so. So you're not seeing such a large displacement. We'll call the limit, and we can also change the shape. Okay. Now we've seen these buckling modes, but how much margin do we have between our applied load and when these buckling modes will be excited? Well, cause collapse of the vessel. So for that, what we need to do is we need to go to the reports, and we're going to go to buckling load factors. See this report here. And what you see is the output that I showed you during the presentation. You see this is a matrix that has been set up with 14 equations, and this is the iterative process. And what you see is after so many iterations, it has found that the lowest 6 have converged. Okay, and you see that for the first 2 load cases, now these were the first order buckling mode, which is roughly a quarter sine wave. This has a margin, or a buckling load factor of 3.8. So that's a factor of around 4. Okay, that means we have a safety factor of 4. So we've applied a load of 1 meganewton, and that means that the column would collapse, buckle, with an applied load of 3.8 times the applied load, so around 4 meganewtons. And if we go back to our presentation, we'll see that if we calculate the Euler buckling mode for this case, you will see, we go through and calculate that the Euler buckling load for this column is around 4 meganewtons. For given the fixed free boundary conditions on the column. Okay, if we then go back to this buckling mode, we see then for the second order buckling mode, the 3/4 sine wave, there's a margin of 32. So chance of exciting that it would always fail with the first buckling mode. And then if we go to the 5 and 6, this was the shell buckling mode, we see there's a very, very large margin. Okay, so what now happens if we were to increase the thickness? If we were to double the radius of the vessel, so we're going to make it 3 meter diameter. Now, if we run this immediately, we will get an error. Why do we get this error? Well, that's because we have not rerun the static case. Okay, so to go back, no. And we're going to submit and wait now. Now you'll see that it will run. Okay, if we run 3D plots, and we can see the stresses, the membrane stresses, due to the applied load. Okay, you see it varies along the length, also due to the weight of the column itself. Okay, so now we want to run the buckling analysis. So we go back to the General tab, and we're going to go to Yes, and let's only plot the first 4 buckling modes. Submit and wait. Now the question is, do we think the buckling load factor will have increased or decreased? Let's go on to reports. And let's go straight to the buckling load factors. And now we see, because of how the eigenvalues are set up in the matrix, it has to compute at least 5, but we see that we have the first 4. And we see that what was a buckling load factor of 3.8 has now increased dramatically. That increase, that factor 8 increase, is caused by the fact that the second moment of area is based on the radius to the power 3. As we've doubled that, so that's 2 to the power 3. And if we go to look at the 3D plots, we can see that it's the same mode, case 1, but you see that because the column is now less slender, then you need to apply a larger buckling load to excite this mode. Secondly, if we look now, let's look at load case 3, we see then that this is the shell mode. So that means that shell mode becomes more critical than the second Euler buckling mode. Okay. Now I think this is enough for the harmonic analysis. I think now let's have a look at the dynamic problem. Okay. So for the dynamic problem, we're going to look at vortex shedding on a tower. So we're going to use the same size column we had previously, a long slender chimney, which is a diameter of 1.5 meters and a thickness of 10 millimeter. And we're going to apply a horizontal wind load of 5 kilonewtons. Simplification that the entire wind load acts. This is the wind load due to vortices, acts along the entire height of the column. Okay, let's open FEPipe to see how we'll solve this problem. FEPipe. And what we see if we look at the input file, if we plot this, is we have the same slender column that we had previously. Plot, look at the geometry, 1.5 meters, thickness of 10 millimeters, and a height of 40 meters. Okay, so we're going to go to the General tab, and we're going to go click on Compute, Dynamic Mode, and Frequencies. Let's get the modal frequencies. Okay, number of eigenpairs. I'm going to calculate. Let's go and calculate 8. This means we've got to calculate the first 8 modes, and we might need to increase the size of the matrix for the eigensolution. Okay, let's submit and wait. Okay. Just running, bear with us, it will be here in a second. Just completing code stressors, and now we can look at the reports. Now let's look at the reports. And what you can see now is you see that's a natural frequency calculation that's been done. Click here. We can see the frequencies of each of the modes. And what you'll see is we've got 8 modes, and we'll see the first 2 have exactly the same frequency, 3 and 4 have the same frequency, 5 and 6, and 7 and 8. Now, let's look at the modes at the same time. So go 3D plots, and once again, as with the buckling analysis, the first 4 cases showed the mode 1, next 4 cases show mode 2, and so on. Look at case 1. What you'll see is this is the first eigenmode. First eigenmode, and this is the eigenmode with the lowest frequency. And this is the simple beam from a fixed to a free end. And you'll see as we move this back and forth, simple quarter sine wave. Now if we look at case 2, what we see is the same mode, but it's the orthogonal pair. That's because it's a cylindrical vessel, there's infinite eigenmodes. Every single place on the circumference has in principle the same mechanical eigenmode. So the eigenvalue problem sets up 2 orthogonal pairs. And this explains why the two have the same frequency. If we then look at I want to look at the second mode, so I need to go to third case. We'll see this is a type of 3/4 half sine wave, and we'll see this also has an orthogonal pair, which is that given in case 4. If we want to look at the additional modes, then we can see down that we can open up additional menus like so. Okay. Now the question is, we want to check, do we actually excite these modes? So we see here, what we can see here though, is the direction of the orthogonal, the two orthogonal eigenmodes. And what you see is it's roughly a 2:3 ratio between the x and the z direction. So what we're going to do to see if we excite that mode is we're going to apply our 5 kilonewton force at roughly 45 degrees to the x direction. Okay, so keeping the same model open, we're going to apply our force in the horizontal plane. So we're going to go to shell boundary conditions, and we're going to add a new boundary condition at the top. So we're going to go top. It's going to be a force boundary condition, and let's apply it as an operating load for now. Now applying 5 kilonewton at 45 degree, so roughly that's 3.5 kilonewton in the x and the z direction. Okay, now we need to go to the general tab, and we're going to go down and we're going to turn off the modal eigen solution. So I'm going to go to no, and we're going to turn on the harmonic solution, yes. And we're going to choose which loads. So if you remember, we selected the operating load, we applied a load to operating load, and we're going to apply the frequencies at which it's applied. So let's do, because we're going to see if we can excite the first mode, which had a frequency of 0.9. Okay, so let's apply these 5 excitation frequencies. As noted, you can do up to 10 different frequencies. Okay, let's submit and wait. Okay, it's almost solved. Great. Okay, well, let's look at, first of all, at the reports. And let's look at the maximum amplitudes. Okay, because we're applying a load at the end. So this will plot the maximum displacement. And if you remember, the first case was at 0.1 Hertz, then we had 0.5 Hertz, stated here, and then at 1 Hertz, we actually have the largest displacement. Okay, see the displacement in the x and z direction changes as we change the frequency of the applied force. Okay, and this isn't surprising given that the eigenfrequency was around 0.9 Hertz. So let's go back and look at the 3D plot. So if we go 3D, and now you see for each of the cases, so case 1 being at 0.1 Hertz, case 3 being at 1 Hertz, you have the local membrane stress and the secondary bending stress. Now, the force will generate a local membrane stress. So let's look at the stresses. So if we stop the slider and we can look at we can clearly see this is plotting the displacement. And we can clearly see that it's exciting the first eigenmode, which had a frequency of 0.9 Hertz. And you see that you've got the largest membrane stress near the anchor at the bottom. We've got the largest bending moment. Okay, so what we're going to do is now compare that with the case where the eigenmode was excited. And we see, if we plot the local membrane stress, if we stop the slider, we see that we excite the same mode, but we've got a much larger stress, local membrane stress, occurring near the base of the tower. So you've got 77 megapascals compared to 14 for the first. Okay, and we can also, as well as seeing the stresses graphically, we can also look at the stresses per load case. So we can go here, let's click the 2, and we see here that we have for each case 15 megapascal, 78, and we see 7. So you see quite clearly the stress that arises in the chimney is very much dependent on the frequency of the applied force. This can be used in your fatigue analysis according to any pressure vessel design code. Okay, so I want to thank you for listening to this webinar, and I hope that you found it interesting and helped you learn how maybe FEPipe could help you solve your buckling or dynamic problems. And if you liked what you heard and want to learn more about FEPipe and how you can best use that, then we invite you to check out our training courses, and we'll give a number this autumn in Houston, in Dubai, and also our offices in the Netherlands. So please consult our website for more details. And if anyone has any questions that they'd like to raise, please feel free. Thank you.